Good morning, chemistry students. Here are your Chapter 14, Day 4 notes. So this is your teaching video. You're going to be picking up in your outline at Trends in Ionization Energy, and we are going to finish your Chapter 14 outline today. So we're going to begin by talking about our trends in ionization energy. You did a chem quest about this yesterday. So again, most of this should sort of be review because it's stuff that we talked about yesterday. So as we start to talk about ionization energy, keep in mind that electrons can move to higher energy levels when the atoms absorb energy. So remember, we talked about this when we talked about the emission spectrum of atoms, that what was happening is those electrons in the atoms get excited, they jump to a higher energy level. They're unstable there, they fall back down to a lower energy level, and they release energy in the form of light when that happens. So you already know that it's possible that an electron can move to a higher energy level when that electron absorbs energy and that atom absorbs energy. Sometimes the electron has enough energy, so it absorbs enough energy to overcome the attraction of the protons in the nucleus. Right? Because remember from yesterday, ionization energy, we're talking about an atom losing an electron. And that happens sometimes because an atom absorbs enough energy that's enough energy to provide that electron with what it needs to overcome that force of attraction of the protons in the nucleus, and basically that atom's going to lose that electron. So the definition of ionization energy is the energy required to remove an electron from an atom. So how much energy do we have to provide to that atom for an electron to have enough energy that it's going to break free of that pull from that nucleus and not be part of that atom any longer? Ionization energies are measured when an element, remember we can use the word element or atom interchangeably, is in its gaseous state. So all we mean by that is we're going to look at this when this element is in its gaseous state of matter, okay? And specifically, the energy required to remove the first electron from an atom is called the first ionization energy. the cation produced has a positive 1 charge. Remember when we learned about ions a couple days ago, we learned about the fact that we can form a cation, which is an ion that has a positive charge. Remember, to be a cation, it means that we have more protons than we have electrons, so we have lost electrons. We also can form an anion, which is an ion with a negative charge. To become an anion, we have gained electrons. We have more electrons than we do protons in the nucleus of that atom. So when we talk about removing this first electron from an atom, it's called the first ionization energy. And because we have removed an electron from the atom, we formed a cation with a positive 1 charge. The first ionization energy tends to decrease from top to bottom within a group and increase from left to right across a period. Okay, and we saw this yesterday when you looked at the ChemQuest, looking at ionization energies. Ionization energies can help predict what ions an element will form. So what I mean by that is you're able to look, you could look at a chart of ionization energies and you would be able to predict what ions a particular element will form. So we're going to actually do that. We're going to take a look at our book at table 14.1 on page 402. This is a table of ionization energies. Specifically, I want you to look at the data for lithium, sodium, and potassium. And it might be easier for you to do this in your textbook if you have your textbook, okay, which you should. Right? We want to specifically look at lithium. It's right here. We want to look at sodium, which is right here. And we want to look at potassium, which is right here. Now remember, when we look at these elements on the periodic table, they're all in the same column. They're all in the same group or family. Okay? So remember, these are the same group on our periodic table. And what you want to notice is that, notice here, we have 520 kilojoules per mole to a jump of 7,297 kilojoules per mole. For sodium, our first ionization energy to remove the first electron, okay, is 495.8 kilojoules per mole. To remove that second electron, it requires 4,565 kilojoules per mole. And for potassium, 418.8 kilojoules per mole to remove the first electron. The second ionization energy is 3,069 kilojoules per mole. So what we're seeing here is we see an increase in the energy between the first and second ionization energies. Okay, and it's large. We see a big increase there. What that is telling you is that it is relatively easy to remove one electron from a group 1A metal atom but difficult to remove a second electron. The conclusion that you can draw from that is that therefore group 1A elements form an cation with a +1 charge. Because it's pretty easy to lose that first electron. It's not easy for it to lose its second. The other thing that we talked about, remember yesterday on our ChemQuest, as when lithium, sodium, and potassium do lose one electron, they get the electron configuration of a noble gas. And remember, that makes them very stable, which means it's very hard to pull off an electron from from that noble gas electron configuration. Notice that when you're talking about beryllium, magnesium, and calcium, right? Those are in group 2A. And notice that that big jump for them occurs between our second and our third energy levels, or second and third, between our second and third electron or electron removal. Remember, for beryllium, magnesium, and calcium, they're in group 2A. When they lose 2 electrons, they get the electron configuration of a noble gas. So remember back here I told you that the ionization energies can help you predict what ions an element will form. Well, what I mean by that is where you see this big jump in amount of energy required, that means that you're going from pretty easy to remove an electron to really hard. And so beryllium doesn't mind losing 2 electrons, but it doesn't want to lose a third, which means beryllium typically is going to form an ion with a +2 charge. Okay, so that's kind of what this chart is showing you. So the group trends with ionization energy, remember we want to look at, remember group we're talking about within the same column, so we want to look at the electron, the Bohr diagram, because that's sort of helpful. So we'll look at lithium, 3 protons, so 2 electrons in its first, 1 in its second, so that's lithium. We will look at sodium, +11. So 2 electrons in its first, it's going to have 8 in its second, and it's going to have 1 electron in its third, and this is sodium. Okay. So when we're looking at the group trends in ionization energy, remember we still want to talk about what's the pull of the nucleus for those electrons in that highest occupied energy level. right? In our first energy level, for lithium, it's +3. There's no shielding. When I get to the second energy level, I have a shielding effect of 2, so my pull is +1. When I look at sodium, my first energy level has a +11 pull because there's no shielding. In our second energy level, I have shielding of 2, so I have a +9. And when I get to my third energy level, I have 2 electrons in my first energy level, 8 in my second, so I have 10 electron shielding, which gives me a pull of +1. So again, kind of as we talk about our group trend, we kind of want to talk about what is staying the same as we move down this group. Okay, notice what's staying the same is the pull of the nucleus for the electrons in our highest occupied energy level. Remember, that was an abbreviation we have been using before, right? Our highest occupied energy level, our outermost shell of electrons. So the pull of the nucleus for the electrons in the highest occupied energy level stays the same. Remember, we talked about this the other day, that in group 1A, the pull is +1. In group 2A, the pull is +2. In group 3A, it's +3. In group 4A, it's +4. In group 5A, it's +5. In group 6A, it's +6. In group 7A, it's +7. In group 8A, it's +8. Okay? So the pull of the nucleus for the electrons at the highest occupied energy level, the shielding also, or the that's kind of staying the same. In terms of what's different, right, the shielding is different. For lithium, there's a shielding effect of 2. For sodium, there's a shielding effect of 10. Because that shielding is different, that's what's leading to the pull of the nucleus for the electrons at the highest occupied energy level to stay the same. Okay? So, the other thing that is different is, right, the number of energy levels. So, in lithium, we have 2 energy levels. In sodium, we have 3. So another thing that's different is the number of energy levels containing electrons. Right, so we have shielding, we have a difference in the number of energy levels containing electrons. So how does this affect, right? Because what we want to talk about here is ionization energy, okay? Pulling an electron off of these atoms. So remember, another thing that is different is that our atom is larger. Right, we talked about that when we talked about atomic size, and the reason the atom is getting larger is because of this number of energy levels containing electron, right? We've added another layer of electrons, which makes our atom larger. So, same between both of these atoms is the pull of the nucleus for the electrons in the highest occupied energy level. What's different is the shielding, okay? The number of electrons between the nucleus and that highest occupied energy level. The number of energy levels containing electrons is different. As we move down a group, we're adding more. And our atom is getting larger, right? So we could even say, maybe better than saying our atom is larger, is a difference is the atom size. Okay. So how does this affect ionization energy? Well, because our atom is larger as we move down a group, because we have more energy levels containing electrons, but the pull of the nucleus stays the same, it is easier. Okay, so as we move down our group, right, our atom size gets larger. Our pull from the nucleus stays the same. but that pull is acting over a greater distance. Therefore, okay, it's easier to remove an electron. Therefore, okay, our ionization energy decreases. Okay, and so again, that's because our atom has gotten larger. The pull from the nucleus is going to stay the same. So that pull from the nucleus is acting over a greater distance, which means it's easier to remove an electron. Therefore, our ionization energy decreases. So that's our group trend. And this is going to be the true whether I'm looking at group 1A or I'm looking at group 7A. This is true for every group on the periodic table. What about then our period trend? Remember, period trend, we're talking about elements in the same group of the periodic table. So we'll look at lithium again with a +3. So 2 protons in the or electrons in the first energy level, 1 in the second. This is our lithium. We will look at boron, which has +5. So 2 electrons and then 3. Okay, so this is boron. And then we can also look at oxygen, which is +8. So we have 2 electrons and then 6 electrons. Again, we want to look at kind of what stays the same here. Okay. So if I want to look again at my pull, right, I have a +3 pull, and then I have shielding of 2, so I have a +1 pull. I have a +5 pull, I have a shielding of 2, I have a +3 pull. I have a +8 pull, I have a shielding of 2, I have a +6 pull. So again, what stayed the same? Our shielding this time has stayed the same. Because we're always adding electrons to our second energy level, we always just have our first energy level shielding, so our shielding stays the same. Okay. Notice what's different again. The pull of the nucleus for our electrons in the highest occupied energy level. Okay. Lithium on the left-hand side of our periodic table has a pull of +1. Boron kind of towards the middle has a pull of +3. And oxygen toward the right has a pull of +6. Okay. So our shielding stays the same. Okay. The pull of the nucleus for the electrons in the highest occupied energy level changes. In fact, right, as we kind of look this way, because that pull is increasing, right, our atom is getting smaller. So another thing that's different is the size of our atom. Okay, our atoms are getting smaller as we go from left to right across our period. So again, remember though, we're talking about ionization energy. So we want to talk about how does this affect our ability or how hard it is to pull an electron off of this atom. Okay? So, remember, we also have, okay, our pull is increasing, which is making our atom smaller. If our pull is increasing, that also means that it's going to be harder to pull an electron off of this atom. right? So because also our pull is increasing, it's harder to remove an electron from the atom. Therefore, our ionization energy increases. Okay. So again, our trend here is an increase in our ionization energy. It's getting harder and harder to pull an electron off of these atoms because we have an increase in our pull from the nucleus, which means it's going to be harder to remove an electron. All right, we also want to talk about then our trends in ionic size. So again, we're talking about how large or how small an ion is. So we talked about ions the other day. During reactions between metals and nonmetals, metal atoms tend to lose electrons, which means that they become a cation because they have more protons than they do electrons. And nonmetals, or nonmetal atoms, tend to gain electrons. So again, remember, we're always starting with neutral atoms that have equal numbers of protons and electrons. So nonmetals tend to gain electrons, so they're going to have more electrons than they do protons, which means that they're going to have a negative charge, and we call them an anion. Cations are always smaller than the atoms from which they form. And we're going to kind of look at why that is in just a moment. Okay? And anions are always larger than the atoms from which they form. Okay. And kind of generally, ionic size tends to increase from top to bottom within a group. So, kind of starting to take a look at these, we know that the metals that are representative elements, remember we're talking about then the tall columns of the periodic table, tend to lose all their highest occupied energy level electrons during ionization. Therefore, and we're going to look at this with a Bohr diagram in just a minute. Therefore, the ion has one fewer occupied energy level. Therefore, the attraction between the remaining electrons and the nucleus is increased. So the electrons are drawn closer to the nucleus. So we'll look at lithium just because it's kind of the simplest one, right? 3 protons, so 2 electrons in its first energy level, 1 in its second. So this is lithium, right? And when we lose this electron, then lithium gets the electron configuration. It still has 3 protons, but now it only has 2 electrons and it has the electron configuration of helium. Okay, so it feels like it's helium. So remember our pull here, right, was +3 and then a +1. So I have 3 protons pulling a total of 3 electrons. Now I have 3 protons pulling only 2 electrons. And the ion has one less occupied energy level. Right here we have the first energy level and the second energy level. Now we only have 1 energy level. Okay? So therefore, the attraction between the remaining electrons and the nucleus is increased, right? 3 protons only pulling on 2 electrons. That means that they're going to be pulling on those electrons more tightly, and we're pulling those electrons closer to the nucleus. So again, our cation is smaller than the neutral atom it formed from. Right? Let's kind of look at the same thing then when we talk about our nonmetals. And I'm going to kind of write in a different color here because it's going to get a little messy and I may have to erase this thing, our picture. So this is the opposite for the nonmetals. The ion, is much larger than the atom because as the number of electrons increases, the attraction of the nucleus for any electron decreases. Therefore, the ions are larger. So to look at that, we will take a look at an atom and an ion that becomes an anion. Okay, so we're going to do oxygen, right, which has 8 protons, so 2 electrons in its first energy level, and 6, 2, 3, 4, 5, 6. Okay, so this is oxygen as an atom. Now, oxygen as an ion still has 8 protons, still has 2 electrons in its first energy level, but to become a noble gas, it's going to be easier for it to gain 2 more electrons out here. 5, 6, 7, 8. So here's oxygen with a 2 negative charge. Right, so here again, my pull is plus 8. I have 8 protons pulling 8 electrons, a 1-to-1 pull. In oxygen as an ion, I have 8 protons pulling now 10 electrons. Okay? And because we're pulling, the protons are trying to pull more electrons. They're not going to hold those electrons as tightly. And so the attraction from the nucleus for those electrons is less, which means the ions are going to be larger than the atoms from which they form. So an anion is larger than its neutral atom. And again, that is because we have the same number of protons trying to hold on to more electrons when we form an anion, which means those electrons are held less tightly and they're going to spread out. So when we talk about period trend, okay, so kind of group trend no matter what, right? As we go down a group, our ions are going to get larger in size. And that's kind of for the same reason as atoms get bigger. Even though they have lost, for the metals, they've lost their highest occupied energy level that contains electrons. They still have added a lithium ion has 2 electrons like helium. A sodium ion has 10 electrons like neon. It still has another layer of electrons on it when it forms its ion, which makes sodium ion larger than a lithium ion. Same thing's true with fluorine and chlorine and the nonmetals, right? We still have more electron shells total filled with electrons. So ions are larger as we go down a group. Okay. In terms of period trends, if we want to compare a lithium ion, right, here's a lithium ion with a +1 charge, to a beryllium ion with a +2, sorry, I wrote lithium, but I meant beryllium, with a +2 charge, right? Notice what's happening here. I have 3 protons pulling 2 electrons. Here I have 4 protons pulling, okay, 2 electrons. Which one of these ions is going to be smaller? Beryllium is smaller because it has more protons holding less electrons. If I look at oxygen plus 8, right, and when it forms an ion, it's going to have 8 electrons out here, so 5, 6, 7, 8. So this is oxygen ion compared to fluorine ion. Okay, oxygen ion has 8 protons pulling 10 electrons total because that second energy level is completely full. When I talk about fluorine with a -1 charge, I have 9 protons pulling 10 electrons. Which one of those is going to be smaller? Fluorine, right, is going to be smaller because it has 9 protons trying to pull 10 electrons. That's going to be a stronger attraction than 8 protons trying to hold on to 10 electrons. So the positive ions, or the cations, decrease in size as you go from left to right across a period. And the negative ions, the anions, also decrease in size as we go from left to right. That brings us to your homework, which is on page 406 to answer questions 6 through 9. Have a good day. Talk to you tomorrow.